Dear students, welcome to Abhyas batch. So these classes will be in English, and in this Abhyas batch, we are going to do some of the very good problems from material science, then metal forming, then metallurgy, then welding and automation. So I am going to cover the questions on these topics, and other topics we have another faculty, they will be covering. So in the crash course we have discussed the fundamentals, and the crash course is in English, and there also we have taken some problem. So in Abhyas batch, what our objective is that you have already done the theory, and some of the questions are average question, the way that appears normal questions in GATE and other examinations. But sometimes in the GATE, some of the very good problems also appears. So in this Abhyas batch, we are going to do few difficult problems also, so that in GATE, even if the most difficult problem appears, you should be in a position to handle it. So in Abhyas batch, we are going to discuss average and little bit difficult problems. And the purpose of Abhyas batch is that you have already covered theory, and these classes will be in English. So today we are going to start with the material science, and these are my qualifications. I am basically gold medal in BTech from Aligarh Muslim University. I am MTech and PhD from IIT Delhi, and I was selected in engineering services 1998, and approximately 1.5 years I worked for the service. And I am also a researcher, and as per Scopus data 2020, I am the top 5% researcher in mechanical engineering. Primarily I work in material characterization and metal forming, and I have close to 200 papers, and that database can be seen on the sciencedirect.com. So these are my credentials, and let us come to the question. So let us do it together. The first lecture that this is a recorded one. Second lectures onwards will be the live lectures. So suppose if you have question, you can type in the chat box. But because of Deepavali, first lecture is going in the record mode. And I would like to acknowledge that these questions are developed by, there is one, the Rohit ji, a very good question. He worked really very hard to develop these questions. The way that sometimes difficulty level comes in GATE, he has really worked hard. So now let us discuss these questions. For an alloys of two hypothetical material A and B, there exists an A-rich phase, there is an alpha A-rich phase and beta B-rich phase. So it's a eutectic system where there is a limited solid solubility, So we will go parts by part. Let us make the phase diagram first. It's a hypothetical alloy of A and B. Let us make the phase diagram. So the phase diagram will be percentage B increases in this direction, temperature is on y-axis, and it is like this, similar to lead and tin, but the question says hypothetical, okay na? So percentage B, on this axis it will be 100% A, percentage B increases in this direction, and on this axis it will be 100% B. Okay, so what our question says, there exists an alpha A-rich phase. Alpha A-rich phase means this is alpha, and a beta B-rich phase. So this is your beta. ठीक है ना? Okay. Find the mass fraction of both phases for two different alloys provided in the table below. Okay. So this is the table given, which are at the same temperature. Temperature is the same. Okay, so first of all, we have to find out, we have to draw the line. 60 per weight percent A, so we have to either see the percentage of B or percentage of A. So 40 weight percent B, mass fraction of alpha is 0.57, mass fraction of beta is 0.43. So first of all, we have to draw a line of 40 weight percent B. So we will do a color change. Let us say this color. So 40 weight percent B. So 40. Now draw the lever R. This is the fulcrum. Okay, this is the fulcrum, and 40 weight percent B, fractions of alpha phase and beta phases are this. Fraction of alpha phase is 0.57, fraction of beta phase is 0.43. So let us do that. And what question is asking? See what the question is asking. Determine the composition of the phases phase boundary. Determine the composition of phase boundary or the solid solubility limit for both alpha and beta phases at this temperature. You know what is the solid solubility? What is the solid solubility? When a foreign element is mixed with any material, it combines in such a way that the resulting microstructure is a single phase. Resulting microstructure is a single phase. That is called solid solubility. So the question is asking, what is the solid solubility limit? I mean, what is the value of X and what is the value of Y? So this is the question. What is the solid solubility of B into A, that is X, and what is the solid solubility of A into B, that is Y? That's what question is asking. So at B, at the first condition, mass fraction of alpha, so lever will be always take the opposite side. Mass fraction of alpha is this divided by the whole thing, meaning y minus 40 divided by y minus x. Suppose I want to calculate the mass fraction of alpha, I take the opposite side, this divided by the whole thing. So let us say this is y, this is x. Now mass fraction of beta is on this side, so we will take the opposite side, this divided by the whole thing. So it is 40 minus x divided by y minus x. So mass fraction of alpha beta is given in the problem. Mass fraction of alpha is 0.57 and the mass fraction of beta is 0.43. So this is the given in the problem. So what you should do now, divide these two equations. So you will get y minus 40 divided by 40 minus x is equals to 0.57 divided by 0.43. Let us say equation number 1. Let us say equation number 1. Okay. Now the second statement. Second statement. Second statement is at 70 weight percent B. At 70 weight percent B, 70% is here. So that's for second condition. This is the fulcrum. Second condition, this is the fulcrum. So here also, mass fraction of alpha and beta are given to you. Mass fraction of alpha and beta are given to you. So for condition 2 means 70% of B, mass fraction of alpha is on this side, we take the opposite side, that is y minus 70 divided by y minus x, and the mass fraction of beta is on this side, take opposite side, means this divided by the whole thing. It is 70 minus x divided by y minus x, and these two values are given to you. Alpha is 0.14, and beta is 0.86. Beta is 0.86. Now you do one thing, divide these two equations also. So y minus 70 divided by 70 minus x is equals to 0.14 divided by 0.86. Equation number 2. Equation number 2. So two equations, two unknown. Suppose if it is a live class, I will give you 1 or 2 minutes so that you can solve and find out the values of x and y. But because it's a recording, I will wait for less number of time. There are two equations. First equation and the second equations. Two equations, two unknown. Find out the value of x and y. Find out the value of x and y. So what is the value of x? What is this x? X is solid solubility of B and A. Y is solid solubility of A and B. So value of x is 9.96%. 9.96%. And beta is 79.8%. 79.8%. So can you cross verify? Can you cross verify? Please cross verify immediately. Please cross verify whether answers are correct or no. So that's what the question is asking. If you see the question, determine the compositions of the phase boundary. So phase boundary, solid solubility alpha is 7.96% and beta will have 79.8% B. 79.8% B. So these questions are really, it was a very good question. It was a very good question. So as we discussed in material science theory lectures, that there are different types of binary phase diagram. First category is isomorphism. In isomorphism, there is 100% solid solubility in the solid state. I like copper nickel phase diagram. Now the second category of binary phase diagrams are eutectics. Where there is a partial solid solubility. So this basically question was from the partial solid solubility or from the eutectics. The most important diagram in this category is the diagram of lead and tin, and iron carbon also diagram also falls in this category. Of course, iron carbon diagram is called peritectic phase diagram. But anyway, it can be fall in this category. There is a third type of binary phase diagram where there is a complete liquid solubility and no solid solubility. Alloys of bismuth follows that type of phase diagram. So that we will skip for this time. Now the second question, please see that. Please read the question once before we move ahead. Please read the question before we move ahead. First of all, go through the question once before I can start solving it. A hypothetical AB alloy of composition 55 weight% B, we will take only B%, because 55 weight% B is nothing but remaining percentage of A. So we will not focus on that. At some temperature is found to consist of mass fraction of 0.5 of both alpha and beta. In the solid state, if there are two phases, alpha and beta, like the previous problem, in the solid state, if there are two phases, it is the second type of phase diagram, that is partial solid solubility. So binary phase diagrams are of three types. Complete solid solubility, that is called isomorphism. Number two, partial solid solubility, that is called eutectics. And number three, complete insolubility in the solid state, that is bismuth. Anyway, those who have time and those who understand a little bit Hindi, because these lectures are in pure English, those who understand little bit Hindi, please see the crash course videos that are available on the YouTube, because there we have discussed a lot of theory related to that. Okay, na? So the phase diagram will appear exactly similar to the previous one. Alpha, beta, percentage B increases in this direction, temperature is on the y-axis. See, generally in the live classes, I see the chat box, and if there is any difficulty, I take care of. Because of the festival, this lecture what I am recording, and it will be transmitted to you on 25th afternoon. So if you have any query, tomorrow, that is 26th, you please write in the chat box, I will clarify. On 26th, because at 26th I will be covering the metal forming. So if you have any query, please write in the chat box, I will take care of at that time. These lectures are 11 a.m. to 1 p.m. Okay, na? So because it is not live, so I will not be able to see the questions the students are having. So tomorrow, 11 to 1 at any time, you can ask the questions. Okay, na? And your tomorrow will be 26th. So first of all, we have to plot the phase diagram. Any question related to lever rule, lever rule, first of all you draw the phase diagram. Any question whatsoever, first of all you plot the phase diagram. Now what the question is telling you, at 55 weight% B, let us say 55 weight% V, this is the fulcrum, so at this point there is a 50% of alpha and 50% of beta. Question says it's a 50% of alpha and 50% of beta. If the composition of beta phase is 90 weight% V, meaning this solid solubility where the beta appears, it is 90%. This solid solubility where a beta appears is 90%. What is the compositions of the alpha phase? In other words, what is this solid solubility X? Why I am saying solid solubility? Because X% B will be completely mixed with A. X% B will be completely mixed with A and produces a solid solution called alpha phase. So we have to calculate X. What is given? Alpha is 50%. So mass fraction of alpha, as I told you in the previous one, mass fraction of alpha means we take the opposite side, this divided by the whole thing. So it is 90 minus 55 divided by 90 minus X should be equal to 0.5. Is that all right with everyone? Now calculate X, and that is answer. Calculate X, that is the answer. Calculate X, and that will be the answer. Calculate X quickly, and that will be the answer. Calculate X, and my answer is 0.2, meaning X will be 20%. So 20% is the answer. See, if the things are live, that are more easy, because we can see the questions of students. We can see the questions of the students if the things are live. So that's it. Question number 2. Okay. Let us say question number 3. Question number 3. Read the question. Read the question. Read the question. A copper nickel alloy of composition 70 weight% nickel and 30 weight% copper is slowly heated from a temperature of 1300 degrees centigrade. So, phase diagram is given. So, this copper nickel phase diagram is an isomorphism phase diagram. Phase diagram is complete liquid solubility and complete solid solubility. Both liquid and in the solid state, there is a complete solubility. So this line is the liquidus line. This line is the liquidus line, and this line is the solidus line. So below the solidus line, it will be single phase, and above the liquidus line, it will be liquid phase, single phase solution. So question number 1 and question number 2 were based on binary phase diagram of category 2. This question is based on binary phase diagram of category 1, that is complete liquid solubility, complete solid solubility, like copper and nickel, like copper nickel phase. Okay, so now this diagram is there. So let us see what are the questions. A copper nickel alloy of composition 70% nickel is slowly heated from a temperature of 1300 degrees centigrade. At what temperature does the first liquid phase forms? At what temperature does the first liquid phase forms? At what temperature the first liquid phase forms? So this is 70% line. This is 70% line, 70% nickel line. Okay. So this is the temperature. Because if I magnify a little bit, solid, liquid, and suppose there is any, let us say X%, this is the liquidus, and this is solidus. So when the sample is cooled slowly, the first solid appears at this point, and when you are heating from the solid state, this is the point at which the first liquid will appear, and this is the point at which first solid will appear. Okay, na? So this is the 70, this is the 70% line. So my question is asking first, at what temperature the first liquid phase will form? So this is solidus. First liquid phase will form at 1345 degrees centigrade. 1345 degrees centigrade is the first liquid will form at 1345 degrees centigrade. Okay. What is the composition of this liquid phase? what is the composition of this liquid phase? You know how to calculate this one? What is the composition of this liquid phase? So, this is a solid S line. Draw a lever arm. Draw a lever arm. जैसे अभी again I will draw it. Again I will draw. So this is the 70%. First liquid appears, and here you draw a lever arm. So this will tell you, if you project this here, this composition will tell you percentage of nickel in the liquid phase. This composition will tell you percentage of nickel in liquid phase. Percentage of nickel in the liquid phase. So from the graph I can see that it is 60%. From the graph I can see that it is 60%. Look at the graph closely. Look at the graph closely. Look at the graph closely. So 60%. So this answer will be 60%. This answer will be 60%. Okay, now the third question is, at what temperature does complete melting of the alloy occurs? Complete melting of the alloy occurs. So here, when we are heating like this, when the temperature goes beyond it, it's a complete liquid. Okay, so when you are heating at this temperature, complete liquid will appear. Complete liquid will appear, and the temperature is 1380 degree. So this question is reading from the graph. So the complete liquid will appear at 1380 degrees centigrade. See here, the temperature is 1380 degrees centigrade. So everything we have read from the graph. Everything we have read from the graph. Everything we have read from the graph. So this is 1380 degrees centigrade. So these three questions I have taken from the binary phase diagrams. In GATE exam, some questions are very easy, but some questions are involving heavy fundamentals. Some questions involves heavy fundamentals. So see what quality of questions these questions are. Now, next question. Read the question and then we will see. Read the question first and look at the diagram. Look at the diagram. What are the indices for directions indicated by the vectors in the following sketch? So direction symbol is like this, na? Directions. I will give you a very brief description here how exactly we plot the directions. How exactly we plot the directions. It's a very, very simple thumb rule. How exactly we plot the directions? Whatever maximum number appearing in the bracket, whatever is the maximum number appearing in the bracket taken as the size of unit cell, and after that, with respect to origin, here this is the with respect to origin, this is your origin. With respect to origin, you mark this point in 3-dimensional coordinate space. You mark this point in the 3-dimensional coordinate space and join that coordinate from the origin. Join that coordinate from the origin, you will get the direction. So here we can see the direction 1. Direction 1. So see here, this is the direction 1. Now, this direction 1 has no relationship with x, so x will be 0. So x will be 0, no relationship with the x, okay na? Now, along y-axis, it is moving only half. Z-axis, it is moving completely. So now, we don't keep anything in the fraction. Let us say the size of unit cell is 2 unit. Size of unit cell is a 2 unit. So x is equals to 0, y is equals to 1, z is equals to 2. Because what I said, maximum number appearing in the bracket, you treat it as the size of unit cell. Identify that coordinate in the 3-dimensional space and join it with the origin. So that's what we have done. So the direction will be 0, 1, 2. So direction 1 is 0, 1, 2. 0, 1, 2. Okay now? Now this direction 2. See, this is the direction 2 for the same coordinate axis. Same coordinate axis, direction 2. So how we will designate direction 2? So this also x direction it is 0. Positive y direction is here. Positive z direction here. Negative z direction will be in this direction. So in the direction 2, nothing has changed. Only the z axis become negative. So this will be 0, 1, 2 bar. 0, 1, 2 bar. See, if this dotted line, if it is showing the dotted line, na, 0, 1, 2 bar will be if the direction is appearing on the same face. Direction appearing on the same face. Direction appearing on the same face. Direction appearing on the same face. For example, this is the unit cell. Let us say one unit cell is kept below. One unit cell is kept below. So this pink color unit box is below. Okay, na? So when This is the direction. Suppose this is the origin. This is 0, 1, 2. And when this is the direction, it will be 0, 1, 2 bar. X, Y, Z. This will be minus Z. But suppose direction is this. Direction is this. Then in this, X will also come. X is equals to 1, Y is equals to 1, Z is equals to minus 2. So in this case, this direction 3 will be 1, 1, 2 bar. So we have to see the coordinate axis. It is very simple. It is very, very simple. Plotting the directions are very simple. Once again, I will repeat. The maximum number appearing in the bracket, take it as the size of the unit cell, and whatever coordinates are given, identify the three-dimensional coordinate, join it with the origin. So, in this previous column, the dotted line, there is some confusion. That is the reason I have plotted here. This will be 0, 1, 2 bar, and if it is like this, it will be 1, 1, 2 bar. Plotting of crystal directions. Okay, na? So, drawing crystal directions and crystal planes are extremely easy. Drawing crystal directions and crystal planes are extremely easy. Okay, na? Now, look at the next problem. Look at the next problem. Derive the planar density expressions for FCC 100 and 11 planes in terms of atomic radius r. Planar density. So, what is planar density? Planar density is nothing but number of atoms on a plane, divided by the area of plane, divided by the area of plane, divided by the area of the plane. And number of atoms we count by the area. So let us see the first problem first. 100. X, Y, and Z. So this plane will be 100 plane, or we don't put comma, okay, na? 100 plane. So there are atoms at each and every corner, and there is one atom at the face. So if you plot it, if you see the hedged portion, one atom is at the center, and there will be corner atoms like this. Okay? And let us the A is the size of unit cell and R is the radius of atom. So this diagonal, can I say A root 2 is equals to 4R? So A is equals to 4R by root 2. This is the relationship between radius of atom and the size of unit cell. So now how many number of atoms here? Central atom, it's a cross section area, okay na? One atom. Now 1/4 atom of this atom will fall in on this plane. 1/4, 1/4, 1/4. So planar density will be nothing but number of atoms are 2 and the area of the plane is a square. So 2 by a square is a planar density. But the question is asking the planar density in terms of radius. Put the value of a here. Put the value of a here. Put the value of a here. You will get the answer. Okay? You will get the answer. So, calculation of planar density for 100 was quite easy for FCC. FCC 100, it was quite easy. Okay? But the second question is, you have to find out the planar density for 111. You have to find out the planar density for 111. Now, what is 111? What is 111 plane? So, again, draw the unit cell. Draw the unit cell. This is our origin. X, Y, Z. 111 plane will be x is equals to 1, y is equals to 1, z is equals to 1. Join these points. This is your 111 plane. This is your 111 plane. Let us say A, B, C. First of all, draw the plane. 111 plane. Now, it's a FCC crystal. It's a FCC crystal. So, on each and every face, there will be an atom. On each and every face, there will be an atom. So, if you plot this ABC, ABC, see BC is lying on this face. So, that facial atom will appear on that branch. Now, this AC, so atom on this face will appear here, and of course, corner atom will be there. Corner atoms will be there. Corner atoms will be there. Now, this facial atom, and this corner atom. Okay. These atoms are 1, 2, 3. These 1, 2, 3 are facial atoms. And 4, 5, 6 are corner atoms. 4, 5, 6 are corner atoms. Okay. So now, what is my planar density PD? PD is number of atoms on any plane divided by area of plane. Number of atoms on any plane divided by the area of the plane. Okay. So, number of atoms, some other color I will choose. Yeah, this one. Half atom, half atom, half atom. Okay, half atom, half atom, half atom. So the facial atom is contributing 1.5 atom. For the calculation of planar density, I see the area. I see the area. So half area of atom, half area of atom, half area of atom. Our simple common sense says that this will be equilateral triangle. Equilateral triangle means this will be 60 degree. This will be 60 degree. And this will be 60 degree. So all the three comes out to be 180 degree. Comes out to be 180 degree. Calls 190 degree. Comes out to be 180 degree. So 360 degree will be one atom. So 180 degree will be half atom. 180 degree will be half atom. So corner atoms will contribute half atom. So total number of atoms are 2. Total number of atoms are 2. See, the things will be very easy. Things will be very easy if you calculate the total number of atoms on any plane. That's it. Game is over. If you calculate the total number of atoms, game is over. Then calculate the area of the plane. Calculate the area of the plane. So let us say A is the size of unit cell. So this will be A root 2. This will be A root 2. Then let us say that is a H. So the area of plane is 1/2 A root 2 into H. A root 2 into H. So this will also be A root 2, na? Okay. So H will be nothing but A root 2 cos 30. H will be A root 2 cos 30. So everything came in terms of A. And that A can be converted into R. So can you tell me what is the planar density? I will give you 1 minute time here. I will give you 1 minute time here. because it's a recorded one, so I don't know how much time you will take. So we have to practice together. Can you tell me what is the answer? Please solve it. Tell me how much answer you are getting. I'm trying to duplicate the live thing here. Okay, solve it. You will get 1 by 2 root 3 r square. Anyway, because see, I am also doing calculations only. So my answer may be wrong, but whatever calculation you are doing, if the mathematics is correct, answer should be correct. Because I am also doing some calculator calculations and all that. So quite possible my answer may be wrong. So don't worry, okay na? Okay. So that was the question on planar density. That was the question on planar density. Question on planar density. Fifth question. Okay. Sixth question. Sixth question. Read the question first. Read the question first. See, in the tomorrow live class, we will, if there is any question, please let me know. Generally in the live classes, I give some time to the students so that they can calculate and all that. Because if you do not practice, you should sit with calculator and rough copy and you should solve with me. Then the learning process will be quick. And if you just watch whatever I'm doing, you will forget. Because already our minds are too much disturbed. So if you want to remember, write. So in these questions, along with me, you should also solve. Then learning process will be very effective. So here, for a 0.35 weight % carbon, for a 0.35 weight % carbon alloy at a temperature just below the eutectoid, determine the following. So I will plot iron carbon diagram in steel range. Iron carbon diagram in steel range I will draw. Temperature and the percentage carbon. Alpha, gamma, Fe3C, and this is 6.67%. 0.02%, 0.8%. All right. So what my question is asking about 0.35%. 0.35%. So this is the 0.35% carbon. So the question is asking fractions of total ferrite and cementite phase, fractions of pro-eutectoid ferrite and perlite, and the fractions of eutectoid ferrite. In the crash course videos, video number 1, we have discussed these things in detail. Okay? So, first, you draw tie line just above the eutectoid temperature. See, the temperatures and composition slightly vary from one book to another book. Composition and temperature slightly vary from one book to another. So now initially you draw the lever arm just above the temperature, eutectoid temperature. The microstructure will be here like this. Grain boundary, it will be pro alpha, and within the grain will be austenite having 0.8% carbon, and the austenite with eutectoid composition is called perlite or perlite. 0.8% carbon austenite is called perlite, and at the grain boundaries whatever alpha is there, it is called pro-eutectoid ferrite. So now this is 0.8, this is 0.02. So mass fraction of pro alpha, we will take the opposite side, this divided by the whole thing, meaning 0.8 minus 0.35 divided by 0.8 minus 0.02. Please remember, if you want to study theory, in the crash course I have discussed some. In the regular batch, of course, we will discuss the complete thing. So mass fraction of pro alpha. Now onwards, I have not calculated. Okay, so I am also doing calculation along with you. You also do along with me. Divide by 0.78, let us say. It is 0.57. So balance will be perlite. So mass fraction of perlite will be 1 minus 0.57, comes out to be 0.43. Little bit calculation we can do from our memory. Okay, we don't have to use calculator. Okay, so that is one. Now draw tie line below the eutectoid temperature. तो उसके लिए अलग कलर ले लो कोई. Draw tie line below eutectoid temperature. This one. This tie line will give you the total alpha. This line will give you total alpha and cementite. So mass fraction of total alpha, because here in the Abhyas batch we are just discussing questions, we are not discussing too many. Through the questions we are trying to relate some fundamentals, but theory we are assuming that you have covered all the theory. So alpha is on this side, take opposite side, this divided by the whole thing, meaning 6.67 minus 0.35 divided by 6.67 minus 0.02. So 6.67 minus 0.35 divided by 6.65, so 0.95. And the mass fraction of cementite will be 1 minus 0.95, means 0.005. Us ayo 0.05. Now total alpha we got and the pro alpha we got. So total alpha will be equal to pro alpha plus eutectoid alpha. You know, what is eutectoid alpha? What is eutectoid alpha? In the parallite, what is the parallite microstructure? Parallite constitute alpha and Fe3C. Alpha phase and Fe3C phase is the parallite microstructure. In the parallite, how much alpha is present is called eutectoid alpha. So mass fraction of eutectoid alpha means total alpha minus pro alpha comes out to be 0.95 minus pro alpha is 0.57. So eutectoid alpha will be 0.38. So see, the all answers came. All answers came. It was a very good problem, really. It was a really very good problem. It was a really very good problem. So between the two problems, I am giving you 15-20 seconds. Another very, very beautiful problem. Very beautiful problem. Question number 7. Please read it. Then we will read together. Very, very beautiful problem. Beautiful, really. जिसकी ब्यूटी बोलना है ना, ये रियली ब्यूटी है प्रॉब्लम की. Find the toughness. What is toughness? Area under stress strain curve is called toughness. Area under stress strain curve is called toughness. For a metal that experiences both elastic and plastic. So elastic and both elastic and plastic deformation, that the modulus of elasticity is given to you. Modulus of elasticity is given to you. And that elastic deformation terminates at a strain of 0.01. 0.01 क्या है? जब आपका yield point आया, sorry, when the yield, I switched over to Hindi because I am taking this crash course that is in English, and this Abhyas is pure English. Okay, no? That's what management asked us to do. So what is this strain? The moment yield point appears, how much was the strain? Is 0.01. For the plastic deformation, assume that the relationship between stress and strain, in which the values of K, N and R, strength coefficient is 6900 and work hardening exponent is 0.3 respectively. Furthermore, plastic deformation occurs between 0.01 to 0.75, at which point fracture occurs. So you have to calculate the toughness. So you read the problem once again, then we will do it together. One more time you read the problem and try to make some diagram out of it. Then we will do it together. It's a really very beautiful problem. Really very beautiful problem. Very beautiful problem, really. So once again you try to draw something in your notebook. Try to do something in your notebook. So stress strain diagram. Oh, I haven't selected different thing. Stress strain diagram. So there is an elastic region and there is a work hardening region. Okay, and it says that This is 0.01 in the elastic range, and up to fracture it is 0.75. This data is given to you. This is the elastic region, and this region is a plastic region. Plastic region. Okay. Then here stress divided by strain is nothing but Young's modulus, and here the stresses are related by K epsilon raised to power n. It's a flow curve equation, simple flow curve equation, and these values are given to you. These values are given to you. Young's modulus is 172 GPa. E is nothing but 172 GPa, and in the flow curve equation, value of K is 6900 epsilon raised to power 0.3 MPa. Now we have to calculate toughness. Toughness means the area under this curve. So how to calculate? This is the straight line and this is the curve. So take one strip d epsilon in the elastic region, and the take of a strip of d epsilon in the plastic range, because in the plastic range curve is different and in the elastic range curve is different. Is that okay with everyone? Is that okay with everyone? So what is the area? It's a simple mathematics. It's a simple mathematics. So the toughness is nothing but the area. So how will I calculate? Integral 0 to 0.01, 0 to 0.01, it is sigma into d epsilon into sigma. Is that okay? Plus from 0.01 to 0.075 sigma d epsilon. This is sigma 2. This is sigma 1. So here we can say that 0 to 0.01, sigma 1 is nothing but E into epsilon d epsilon plus 0.01 to 0.075 K epsilon raised to power n d epsilon. It's a definite integral. It's a definite integral giving you 1 minute. Can you solve it manually? Also, it is not a very complicated integration. I need the answer, total area, or you can say the toughness. I need the total answer. I myself solved this one. I need the answer. Giving you 1 minute. Can you just quickly solve it? Quickly solve it and give me the answer. Quickly. Use calculator. Use calculator. And more quick you are, it will give you one upper hand advantage in GATE exam. It will give you advantage in GATE exam. Okay, quickly do it. In Telugu, we call it Tondarka Cheyandi, because this English is seen by students from Telangana, Andhra, Karnataka. So, Andhra, Telangana, Telugu is a very sweet language. Tondarka Cheyandi. Okay, na? So, if you are quick, gate, it will be your advantageous position. Okay, na? This answer we have calculated as 3.65 into 10 raised to power 9 joules per meter cube. That is the answer that will come. So check whether it is okay. Check if it is okay. It was a really very beautiful problem. In gate, whatever this problem and the next problem, and the metal forming basics. So a lot of overlap question comes in gate. Lot of overlap question comes in gate from the metal forming introduction and this theory of plasticity, sigma f is equals to k epsilon raised to power n. So I hope all of you are getting the same thing. Next question is little bit easier than this. I want you to give me the answer without my help. Next question is easier than this. I want the answer without my help. Go through the question and then we will discuss if there is an issue. But I think without my help, you will be in a position to answer this. Without my help, you will be in a position to answer this. Tensile test is performed on a metal specimen and it is found that a true plastic strain of 0.2 is produced when the true stress 575 MPa, the curve will go a little up. Can we delete it, erase? Yeah, okay, good. It's working. Because only yesterday itself I started using this software. I was using some different thing, PPT. So I'm just learning it, okay? The software, how to reception, how exactly it goes. For the same metal, the value of K is strength coefficient sigma F is equals to K epsilon raised to power n. Value of K is 860 MPa. Calculate the true strain that results from the application of a true stress of 600 MPa. Let us say if the true stress is 600 MPa, what is this true strain? What is this true strain? So sigma F is equals to K epsilon raised to power n. This first boundary condition you apply. So 575 is equals to 860, epsilon is 0.2 raised to power n. Calculate n from here. Do it. Calculate n from here. Please do it quickly. Calculate n from here. Calculate n from here. Calculate n from here. Calculate n from here. My answer is coming 0.25. Check whether it is okay or no. My answer is coming 0.25. Check whether it is okay. My answer is coming 0.25. Check whether it is okay. Okay? If it is okay, let me know. If the check if it is okay for you. If it is okay for you. Now apply the same thing to condition 2. So sigma f is equals to k epsilon raised to power 0.25. Stress is 600 is equals to 860 epsilon raised to power 0.25. Calculate epsilon 2. 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 My answer comes out to be 0.237. This numerical, you have to be little quick. Numericals, you have to be little quick. 0.237 is my answer. Let me know whether you are getting the same thing. Once again, because it's a recorded one that is going, it is recorded one that is going. So if there is any queries, you ask me tomorrow, that is 26th, 11 to 1, I will be live. 11 to 1, I will be live. So if there is any query, you let me know at that time. Okay? All right. Question number 9. For a 0.35 weight percent carbon alloy at a temperature just below the eutectoid, determine the following. So, question number 1. This is your 0.35. Okay. We have to find out the total ferrite and cementite phase. This is the fulcrum. 0.02, 6.67. We are discussing first one. Mass fraction of total ferrite will be nothing but opposite side, na? 6.67 minus 0.35 divided by 6.67 minus 0.02. This type of problem we have done for 15-20 minutes before. 6.67 minus 0.35 is equals to divided by 6.65. 0.95. And the cementite will be 0.05. So answer first is correct. First is correct. Okay. Easy, na? Easy. The fractions of pro-eutectoid, ferrite and perlite so here take the tie line above. This is 0.35 because this region is alpha plus gamma. 0.02, 0.8. So this second case will give you pro alpha and perlite. We discussed such problem before, na? It's a slightly different composition so that you get practice, because in the gate sometimes these problems may appear. That is the reason we have given two problems. So mass fraction of pro alpha, alpha is on this side, take opposite side, this is the fulcrum. 0.8 minus 0.35 divided by 0.8 minus 0.02. Mass fraction of pro alpha. 0.8 minus 0.35 is equals to divided by 0.78. 0.57, and mass fraction of perlite 1 minus 0.57 comes out to be 0.43. So see which option is correct. See which option is correct. 0.57 and 0.43. This one. This also option 1 is correct. This also option 1 is correct. Total ferrite is 0.95, okay na? So you have to calculate eutectoid ferrite. Total alpha is nothing but pro alpha plus eutectoid alpha. This is 0.95. Pro alpha is 0.57 plus mass fraction of eutectoid alpha. So mass fraction of eutectoid alpha will be this minus this. .38. Yeah, this one. You know why there is a slight variation? Because the composition and the temperature, as I told you before, composition and temperature slightly vary. Composition and temperature slightly vary from one book to another book. So you should not worry too much about this. You should not worry too much about this, and this is the solution. This is the solution. Okay? This is the solution. So this problem was relatively same as the whatever we have discussed before. This problem was same. Let us see next variety. Very, very beautiful problem. Very, very beautiful problem. This problem is related to dislocations. This problem is related to dislocations. Read the problem first. I will give you 1 minute time. I will give you 1 minute time so that you can read this problem. Very, very beautiful problem. This problem will clear all your fundamentals of dislocation theory. I have 3 videos on YouTube. Type my name, Shwadesh Kumar Singh, dislocation theory. 3 videos will come. Those 3 videos, see minimum 3 times. See minimum 3 times. Okay, no, very, very important videos, because one time you will not be able to follow anything. Dislocation theory is one of the most difficult section in material science. Dislocation theory is one of the most difficult section in material science. So now I am reading with all of you. Okay. In the edge dislocation configuration given in the figure, see these are the dislocation. Oh, I will change some red color kind of thing. Pink is better. One dislocation is here. Another dislocation is here. Okay. In the edge dislocation configuration given in the figure, dislocation X and Y are fixed. You know what are the fixed dislocations? Because you know I have not taught you theory, but I am doing the questions. Okay. Because the Abhyas batch is for the one, those who have already understood the theory properly. Within the grain, let us start in this way. I will teach for 2-3 minutes. I will tell you some fundamentals. Dislocation is very, very important, and every in mechanical engineering, mechanical, PI, metallurgy people, they should understand dislocation by heart. Every mechanical engineer, metallurgy engineer, XC, whoever, PI, you can give the gate by PI, XC, mechanical, metallurgy. Everyone out of these four, they should understand dislocation theory by heart. Otherwise, there will be problem during interview. If you know dislocation theory, interview will be very easy. See, whatever load we apply on the material, whatever type of, whether tension, compression or shear, a component of that load appears as a shear stress normal to dislocation line. Normal to dislocation line. And this is called resolved shear stress. So when the stress increases, resolved shear stress will also increase. And the stress at which dislocation begins to move in the material, the stress at which dislocation begins to move in the material is called critically resolved shear stress. Critically resolved shear stress. So now the moment, now hear carefully, the moment dislocation begins to move in the material, number of dislocations multiply. How exactly number of dislocation multiplies? There is something called Frank-Reed source. There were two scientists, Frank and Reed. Generally, the way it happens in the academia, student work he will show to his teacher, and when the teacher approves, his name is also added. So one is a student, another is a teacher. Like Bose Einstein. Bose is a genius Indian researcher, but at that time Einstein was the top scientist in the world. So he has given some equation Bose and given to Einstein. That can you see whether it's okay? So Einstein changes little bit here and there, and that equation is later on known as Bose-Einstein equation. Physics, you must have studied that one. So Frank-Reed source, same story of Frank-Reed source. Number of dislocation multiplies. The new dislocation that is coming up, they do not move. In the theory class, we will discuss separately these things. So this X and Y are the dislocations that are not moving. Probably these are the dislocations that are generated by the Frank and Reed source. So the X and Y, these dislocations are not moving. Keep on reading. The two slip planes are separated by a distance h. So this is one slip plane. See, this is one slip plane, this is another slip plane, this is one slip plane, another slip plane. Two slip planes, and in between two slip plane, h is the distance. H is the distance between the two slip planes. Now, there are dislocations here. See here, one dislocation here, another dislocation here. Now these dislocations are gliding over it. These dislocations are gliding over it. So now, understood? First plane, second plane, these dislocations are locked. These dislocations are free to move. Now the question is asking which option is correct. I will give you some insight. See, the dislocation looks like this. Dislocation looks like this. Now this dislocation is locked and cannot move in this direction, X and Y. But suppose another dislocation is coming from here. From here the dislocation will be easily able to move because there is no obstruction. Interaction between the two dislocations are repulsive in nature. So these dislocations will not be able to move through this path because these dislocations are locked, and the interaction between the two dislocations are repulsive in nature. But on this plane, that these dislocations will glide. So the position of these dislocations will be unstable. Unstable means will keep on moving. So option A is correct. Position 1 unstable, position 2 unstable, position 3 unstable. Means all the positions are along this line. These dislocations will be unstable and will keep on moving, because there is no obstruction. Interaction between the two dislocations are repulsive in nature. So anyway, because I have not taught you complete material science and dislocation theory, so this question will be little difficult to handle. So that's the reason I'm quickly glancing over it. See the next problem. And before teaching you the next problem, there is something called critically resolved shear stress. Critically resolved shear stress. What is the critically resolved shear stress? Critically resolved shear stress, what is that? As I told you, whatever stress you are applying on the material, a component of that stress appear as shear stress normal to the dislocation line called resolved shear stress. And the moment dislocation start moving, that stress is called critically resolved shear stress. So critically resolved shear stress is nothing but sigma cos phi cos lambda, and the sigma is the applied stress. So different component you should know. Sigma is the applied stress, phi is the angle between normal to the slip plane, angle between normal to slip plane and the applied stress, So sigma is the applied stress, phi is the angle normal to the slip plane and the applied stress, and this angle lambda is angle between slip and the stress direction. Angle between slip angle between the slip and the stress direction. So critically resolved shear stress, that is a way to calculate. Now read the question. This formula you must have mugged up in your graduation or from wherever you are studying material science for any coaching. Now how to apply this formula we will learn. Considering a single crystal, read the question. Please read the question, then we will move forward. Please read the question. Please read the question. So, consider the single crystal BCC iron oriented such that tensile stress is applied along 0, 1, 0. Now, compute the resolved shear stress along 1, 1, 0. Okay, so our phi will be calculated between 0, 1, 0 and 1, 1, 0. Direction 0, 1, 0 and 1, 1, 0. That's the definition of phi. Direction when the tensile stress 52 MPa is applied. 52 MPa is applied. Okay, na? If the slip occurs, now slip occurs at 1, 1, 0 and in this direction. So now what is my lambda? As per the definition of lambda angle will come in 1 bar 1, 1, 1 bar 1, 1 and 0, 1, 0. this will remain same. So first statement will give you the value of phi, second statement will give you the value of lambda, and the problem will be easy. So how exactly we calculate? Let us say cos phi. Let us say cos phi. I think next page will be better, otherwise there will be too much hodgepodge here. So 110 and 010, यही है ना? Yeah, correct. So this is U1 V1 W1, U2 V2 W2. U1 is equals to 1, V1 is equals to 1, W1 is equals to 0, U2 is equals to 0, V2 is equals to 1, W2 is equals to 0. Then it is cos theta is equals to U1 U2 plus V1 V2 plus W1 W2 divided by underscore U1 square plus V1 square plus W1 square, U1 square plus V1 square W2 square into U2 square plus V2 square plus W2 square. Okay, so this is the common formula theta. Now you have to calculate phi. So cos phi is equals to U1 U2. So 1 into 0 is 0, V1 V2 1, W1 W2 0, divided by under root U1 square means 1, U2 square is 1, U3 W1 square is 0, 0 plus 1 plus 0. So cos phi is equals to 1 divided by under root 2, 1 divided by under root 2, correct na? So phi is equals to 45 degree. Calculate. So similarly lambda, first of all you complete this one, whether it is okay or no. Just let me know whether it is okay or no. I think for most of you there will be a shock because you might not have seen these types of problems before. So that's how we calculate phi. And for lambda, U1 better is next page. Next page will be better. For lambda, U1 V1 W1, U2 V2 W2. So what are the coordinates? -1 1 1, -1 1 1, and 0 1 0, 0 1 0. So cos lambda is U1 U2 0. अरे ये क्या हो रहा है? V1 V2 1, W1 W2 0. Okay. Now calculate this one. Under root 1 plus 1 plus 1 plus 0 plus 1 plus 0. So cos lambda comes out to be 1 divided by under root 3. So lambda, do it. How much is the lambda in that? How much is the lambda in that? How much is the lambda? So phi we have got and the lambda we have got. Phi we have got and the lambda we have got. It's a 54.7 degree. Okay. Sometimes this software gives some error. So, we don't know. It behaves a little erratically. It behaves erratically sometimes. So we have got phi, we have got lambda. We have got phi, we have got lambda. Okay. Now, check this one. we have to calculate the result shear stress. And for result shear stress, applied stress is 52 MPa. So answer A will be like result shear stress is sigma cos phi cos lambda, cos phi and cos lambda. So we have to calculate 52, result shear stress is 52 cos 45 cos 54.7. You will get result shear stress value. Calculate what is the answer. Calculate what is the answer. Please calculate what is the answer. Please calculate. Please calculate what is the answer. For some of you, they may not have studied in your BTech unless until you are from IITs. Nobody teaches material science properly, including most of the coaching institutes. They don't teach material science properly. So you have to learn properly. This my answer is coming 21.3 MPa. 21.3 MPa. That is the answer for first question. Answer for first question. That is the answer for the first question. Answer for the first question. Now, what is the second question? Second question, if the slip occurs on this plane and critically resolved shear stress is given to you 30 MPa, then calculate the magnitude of the applied tensile stress. In other words, question is asking you to calculate what is the yield strength and if the critically resolved shear stress is 30 MPa. So B, critically resolved shear stress is given 30 MPa and you have to find out what is sigma. So 30 is equals to sigma cos 45 cos 54.7. So find out sigma here. That is the answer for the B problem. That is the answer for the B problem. Do it and give me the answer. Give me the answer. Calculate and give me the answer. .4 MPa. If it is live, it will be different mechanism altogether. I will ask, some people will answer, I will correct. So it's altogether different mechanism when the lectures are live and the questions when I'm solving it is live. But anyway, because of Deepavali festival, we cannot do anything. So that was the question on critically resolved shear stresses, how to calculate. How to calculate the critically resolved shear stresses. How to calculate the critically resolved shear stresses. Okay. Now next three questions are very, very easy. Give me the answer here. It's based on TTT diagram. It is based on TTT diagram. It's a portion of TTT diagram. If my cooling rate is like this, what I will get here? That is the answer. This TTT diagram is a start of decomposition. Okay. This is the finish of decomposition. Finish of decomposition. Yani this is the 0% decomposition and this is the 100% decomposition. 0% decomposition and 100% decomposition. So if I draw the 50% decomposition line, this will be like this. 50% decomposition line will be like this. See? So at this point, there will be 50% perlite and 50% austenite, because we are entering the TTT diagram above the nose. We are entering the TTT diagram above the nose. So austenite will convert into perlite. So 50% perlite will convert. But this austenite will not change up to this point. Even up to this point, 50% austenite will remain in the microstructure. This is the martensite start line. This is the martensite finish line. And we are quenching up to this temperature, that is room temperature. So this austenite will convert into martensite. And perlite will remain as it is in the microstructure. Because in TTT diagram, you know what is the thumb rule? What is the thumb rule? Once austenite converts into some other microstructure, it never reconverts again. So it's a 50% martensite and 50% perlite. Answer is D. 50% martensite and the 50% perlite. Answer is D. D for Delhi. D for Delhi. D for Delhi. Okay? Easy, na? Once again, I request you please see my material science crash course lecture if you want to study theory. That is a crash course only. Okay? Yeah. Question number 13. We are assuming, and these are difficult questions. These are not easy questions. These are difficult questions. Okay, na? In the absence of any external stress, which one of the following statement is related to interaction of point defects? Interaction of point defects and the dislocations is false. Again, there is a dislocation theory, and it's a very difficult question. Very difficult question. So, out of this 4, 1 is wrong, 3 are correct. An oversized solute atom would preferentially migrate below the slip plane of the edge dislocation. It's a correct statement. You know why? Suppose this is the dislocation. This is the dislocation. Now here, these atoms will be under tension. So because of overstretching, the interstitial voids will be slightly larger. So it will be below the slip plane of the edge dislocation. It's a correct statement. A spherically symmetric point defect can interact with both the hydrostatic and shear stress field of the dislocation. Problem is that a spherical symmetry is almost difficult to get it. In theory of plasticity, there is something called, in the metal forming, in the crash course metal forming, I had told you what is the hydrostatic component and what is the deviator. Shear stress is also called deviator component. So, spherically symmetric point defects can interact with both the hydrostatic and the shear stress field of dislocation. It's a wrong statement. It cannot interact with both. Okay, na? So option will be C and D is also correct. Point defect can locally modify the elastic modulus. That's correct. Because if there's a point defect, it creates a localized strain field, and these localized strain field creates obstacles in the movement of dislocation. So it's correct. Modify the elastic modulus. It's a correct statement. Vacancies are attracted towards the compressive region of the dislocation. Where is the compressive region? This is the compressive region. So vacancies will be attracted towards that, and the point defects will be attracted towards tension. So its answer is B. I mean, A, C, D are correct. B is wrong. Very beautiful problem. Once again, in Abhyas, our target is to give you 50% average problem and 50% difficult problem, so your fundamentals are clear. But as we are not teaching theory, we are just covering some fundamentals. Purposefully, we are not doing theory, because otherwise it is impossible to cover the whole thing. So we are assuming that the theory you have covered fully. Last problem for this lecture, and tomorrow I will take up metal forming 1. In Abhyas, material science only 1 lecture, metal forming 2, metallurgy 2, welding 1, and automation 1. 14th, it's a MSQ, multiple select question. It's a multiple select question, so multiple options are correct. So please read it and then let me know if you are able to hit the problem. Please let me know if you are able to hit the problem, hit the answer. So, reduction in strength and hardness occurs after long period of time is called overaging. If you see the aging curve, hardness versus time, it is like this. Okay, na? And this is the region of overaging. So A statement is correct. It's overaging. Sudden quenching increases the impact strength. It's wrong statement. Sudden quenching will produce brittleness, and the brittleness, slight amount of impact, it will break. It's a wrong statement. Annealing is done to elevate the plasticity in metal, because annealing is done to increase the ductility. So this C statement is correct. Carburizing is done in low carbon alloys. Bilkul sahi hai. So carburizing, what is the carburizing process? It's a process of diffusing carbon in the outer surface of mild steel specimen. Because mild steel specimen, carbon is not sufficient to facilitate hardening process. So we diffuse carbon. So it is done only for mild steel. So for A, C, and D are correct here. So that was Abhyas questions for material science. Let us see tomorrow. If you have any question on this, please interact live with me tomorrow 26th. Thank you very much.